Okay, I want to talk a little bit about the concept of lag. So we have the same data set that he has open, the airline passenger data. Okay, so here in his video, he's creating the new date based on A2, which was the old date. But as we can see, the old date is not really a date. So he wants to convert it into something that looks more like a date. So this was something like the number of seconds from like 1970 or something like that. So that's the way the data was originally recorded. Kind of a strange way to record it, but that's the way it was recorded, or that's the way it's been transformed. Anyway, that's the way we've received it. So he comes up with this formula. So he takes the data, it was in milliseconds, not in seconds. So he takes the data, and then this is, I guess, the number of milliseconds in a year. And this is an extra factor there for, or an extra piece here for the fact that we have leap years. So he takes, there's 1,000 milliseconds in a second, and then there's 60 seconds in an hour, and 60 seconds in a minute, and 60 minutes in an hour, and 24 hours in a day, and this many days in a year. So if he divides by this is the number of, this is like a 1 day, and then he adds 21. I'm sorry, this is the number, this is a year, and then he adds 21 to bring it up to some, I don't know, the starting point of when this particular data was begun, and then he multiplies by 12 to get the number of months. So this is an example of a derived variable because maybe this A2 is not so useful, and we'd rather have it in this form. So I think I have the right formula here. I'm using the add expression, which we mentioned at one point earlier in the course, what can be used to create derived variables within Weka instead of doing it, say, in Excel. And it's an unsupervised filter, and it's an attribute filter. So anyway, here it is. He calls it new date. So I'll do that and run it. And I did something wrong. So I put in this extra 25 here. I guess that's what's wrong. Let's see. Try it again. Okay. So now new date goes from basically from 0, which is basically where we wanted to. That's why we had to add the 21. If we didn't do that, it wouldn't have started at 0. And if we look at it, we can see that new date is 0, then 1 month, then 2 months, basically 3 months, basically 4 months, basically. So it's almost right. So that's good enough. So it's the number of it's a monthly data, and it starts at 0 instead of what the original one started at some weird number like this. We can't really see it here. Can we? No. Then I think he removes this one, so let's remove that. And let's try linear regression. And we need to predict passenger, not new date. And we get the root mean squared error. So there, we didn't talk about exactly what this means, but it's just a measure of the error, how the dots fall away from the predicted line, the regression line. So currently it's 46 point something, which is the same as his. So it's called the root mean square error. So it just means we're taking all this data, and here's the regression line, and we're just measuring how far is this from the regression line, how far is this from the regression line, how far is each dot vertically from the regression line, and then we actually we square those distances, and we did talk about that at one point. we square all of those distances, add them up, and divide by the total number to get the average squared distance from the line, and then we take the square root because we squared everything. So it's called the root mean squared error. So it's a kind of measure of how far away all these dots are from this line. Okay, now in this video, which is the before he jumps into the forecast tab, he then uses another filter called time series translate, which is an unsupervised attribute filter, and this is he's going to do the lagging. So let's try this and talk about what the point is. So the first thing he does is he makes a copy of the passenger numbers, and he does that with this filter here, and it's an unsupervised attribute filter. So I have it here, and we're just going to make a copy of, we have to say which attribute, so it's currently called, it's A1 here, the passenger data. So let's do that. I guess it just wants a 1 there. Okay, so now we have this copy. So let's just look at this, see what it looks like. So it's exactly the same, 112 here and so on, and the same data here. We just made a copy of that attribute. So that's not very useful by itself. But now he's going to use this time series translate. So basically we're going to take what we have here, we're going to take these and we can either, I guess we could either shift them up or shift them down. We're going to shift them down. So like this whole column is going to be shifted down a certain amount. It's like in Excel, you could just select the whole column and then put the pointer up above and just drag it down. So that's the kind of thing we're going to do. And then we're going to talk about what's the point of that. So it's an unsupervised attribute, I think. What was it again? Unsupervised attribute time series. Unsupervised attribute time series translate. Okay, let's do it first and then see what it does. Okay, so what is going on here? Why did we do this? So what we're saying is we created this new variable, and this value is here. So let's ignore the first 12 instances, and let's start here and think about what's going on. So here we were saying that we had one before we created this variable, we had one input here predicting this output. So this was the month, and this would predict the output. This was the month, and this would predict the output. Okay, now what have we done? So now we have another variable that we're going to use to predict the output, the passenger numbers. And what is this number? This is the number of passengers exactly 1 year ago. So when we do this, we're suggesting that the number of passengers 1 year ago has some predictive value in trying to predict what the number of passengers are exactly 1 year later. Same thing with here. This is the number of passengers 1 year ago, has some value in predicting the number of passengers now or at this period. So when we do this, we are testing to see whether what happened 1 year ago has some predictive power in terms of what's happening right now. So if there's kind of a yearly pattern, then this will pick it up because it'll be in here, and then we'll use this to predict what's going on here. Okay, now it's possible to add in, instead of using minus 12, we could have used, say, positive 12. But that would not make any logical sense, because then, instead of moving everything down, we'd be moving it up to here. So what we'd be saying is, like, down here, whatever this is, maybe 24, maybe this number here, 118, can be used to predict this number here. But that doesn't make any sense. That's saying that the data in the 24th month can be used to predict the data in the first month, but that's useless. We can't use future data to predict what's going on now because we don't have future data. Of course, in a historical data set, we do have future data, but if we want to use our model to predict what's going to happen tomorrow, we can't do that because that would say we're using data 1 year from now to predict what's happening tomorrow. Obviously, you can't do that. Not in this universe. So it doesn't make sense to put a plus 12 here or a plus 1 or plus anything, because that would be moving it up. And also, we could put in minus 1 instead of minus 12. So what would that mean? That would be just moving it down one level. And so then we'd be saying that what happened in the previous month, 112, has some predictive value on what's going to happen this month. So that sounds reasonable. And so that might be a good thing to do. We could also, suppose we thought that what happens at the beginning of the season is affected by what happened at the beginning of the previous season. So I don't know, when does summer begin? I'm not sure, but let's say summer begins in June. Then the previous season is spring, which must begin 3 months earlier. So that would be March, I guess, right? March. So we might think that what happens in March has some effect on what happens in June. Then we would want to shift down 3 units instead of 12. Okay, so, and you recall that, or you'll see that the forecast button here does create all of those variables. So it creates a minus 12, a minus 11, a minus 3, a minus 1, and so on. It creates many of them. And then what it does is it tests using attribute selection to see which of those are important in predicting passenger numbers. So it filters out the ones that aren't useful. So it seeks to find out which ones are useful among all of the lags that it creates. Remember that these lags are all derived variables. So we hope, just like when you create the derived variables, that they have some value in making the predictions. But they might not all have value, and then you can use attribute selection to filter out the ones that do and the ones that don't. Okay, now he wants to remove the data that is basically has missing values. So these all have missing values basically because these values are missing. So we're going to use this column as part of our set of input variables, but this column has some missing values. So he wants to clean that up. So he's just going to cut out this block of the data and then just start it from here. Of course, we'll lose a little bit of data, but we do gain this, maybe some predictive value from this particular variable. So he uses this remove range, which is an unsupervised instance. This is, I guess it's 1 through 12, 1-12 maybe. And let's try it. And okay, so we're starting, you can see this was originally in the 13th row. Now it's we removed the first 12 rows, so now it's in the top. And we can assume that all these have been shifted up properly. Then we can run it again. And actually, let's see, what did we have last time? This was without the lag variable. So it was 46. Start it again. So it's dropped down quite a lot. So that shows that one lag of 12 months, that there is a strong relationship between what happened now and what happened 12 months before, which let's look at that. So if you want to read a little bit about this, you might look at towardsdatascience.com and look up this, econometrics approach to time series analysis. So they have, I think this looks pretty good. And we can talk about something called seasonal decomposition, and then time series components: trend, seasonality, cycles, and residuals. So trend is, this is the trend, the red line would be called the trend. But there's also seasonality. So that's the fact that the lag of 12 months is predictive. That means that, like, what happens at the beginning of the year, say in January, is going to happen again in the next January. So that's called seasonality. They say variation in data caused by seasonal effects. For example, ice cream sales are high in summer. Heating oil sales are high in winter but low in summer. So in that case, the lag of 12 months would be important to do. Cycles are periodic variation due to economic movements. It's different from seasonal variation. The cycle is the variation of autoregressive component. Cycles occur within longer time intervals, such as every 6 to 10 years, whereas seasonal variation occurs in shorter time intervals. Okay, so that's another part of the time series that we might want to consider. And the residuals is just, after we form our model, how much is left over. So right now with just this model, there's a lot left over. But if I think he shows a different model later on in this video. So here he shows this blue line is also a model. Now the residuals off of the blue line are much less. Okay, so that means the error is going to be much better, much less for the blue line model than for the red line model. And the blue line model is actually what we've generated in Weka at this point, because we added this lag. So we've picked up the seasonality, which is what is being shown here. We picked up the seasonality, and so we reduce the error a lot. The error goes down. Now, I wish we had a lot of time to talk about this, but you can read in here. I think it'll probably be quite clear. Anyway, that's what's meant by the residuals. So a component that is left after other components have been calculated and removed from the time series data. So we kind of say that we've removed, in a sense, we've removed the seasonality from the data, in the sense that we've picked it up. That's what it really means. But to say that it's removed, it means that it's removed from the error. So whereas before we had big error, which was error off of the red line, now we've removed the seasonality component from the error, and so the error is much smaller now. It's only the distance to the blue line. Now, he shows some visualizations here, but they seem to be kind of hard to understand. But we can get some good visualizations once we use the forecasting tab. Then we can get a lot of good visualizations. Once again, I just want to mention that when we use the forecast tab and we just let it run by itself. Let's see, maybe we should do this again. Okay, so I'm starting again with the data. I reloaded the data and click here and just click start. And you can see up here that all of these lags have been created. So it's going to try and build a model based on all of these lags, but it might filter out some of them, as we said, using some kind of attribute selection. So actually, the model that it finally figures out is this one here. Now, this looks pretty awful, so maybe I'll just mention what this is. But look at this thing. So actually, I think he also makes it easier. So we can, let's, instead of trying to understand this crazy thing, this just looks too confusing. Let's, in terms of lag creation, let's use custom lag lengths and only use one lag. So we don't get all of these. We only get from 12 to 12. That's just the 12 unit lag. And here we will remove leading instances with unknown lag value. Okay, that's the one we did that manually, so we can do that here. And then we're going to, it creates this one, powers of time. So what is that? Let's just look at it. So here we have the time, the date is the time, but it has, that's fine. Date is good. We want to include the date. But it also has a derived variable, which is the date squared. Now, why should we include something like that? It doesn't seem like it has any usefulness. It might actually, but it doesn't seem like it would. And this is even the date cubed. Seems like an even weirder thing to include. But anyway, Weka creates that here. But let's get rid of some of this complication. I just want to explain what this model means. So I don't want to have all this stuff in there. So included products, and then it does some more stuff. We don't want all of that. So let's just click OK and try it again. Okay, so now it doesn't create all of that stuff for this model. So you can see it only created these instead of the previous time. Created a whole lot. All of this stuff. All of these. Okay, so anyway, let's just look at this one. So what is the model that we get? So how many variables are there altogether? Here, this is how many we start with. I'm not sure how many it uses in the model. It might filter out some through attribute selection. So let's see, what does it do? It doesn't filter out much. It looks like it uses all of them. So it uses there's 1, 2, 3, 4, 5 possibilities, and I guess they're all here. Not quite, it's a little bit different. Okay, anyway, this is much simpler to look at than the other one. So what is this anyway? So here it is. I copied it into Word. So let's still even make it simpler. Let's just suppose that somehow it worked out to just look like this. Let's get rid of, let's just use these just to make it look easier. Let's get rid of that. And suppose it looked like that. Okay, suppose it looked like this. All right, so before, if we had done it just a regular regression, not done any of the lags or anything like that, we would have like passenger numbers, I'll just call it that, passenger number equals, and we'd have the date, what did we call it, new date, time, maybe times 5, I'm just making this up, plus 25 or something like that. So that would be a linear model. So we have, so if we know the date, we'd put it in here, multiply times 5, add 25, and that would give us the prediction for the passengers. Okay, and this is just what we call a linear model, just of the form y equals mx plus b, which is an equation of a line. So x is this, and m is the 5, and b is the 25. But of course we know that in data science we want to be able to use many variables, not just one variable, not just this, or not just a single variable x. So so we could have, for example, let me stick with this notation. So we might have y equals, and I'll call it a0, instead of b, I'll call it a0 plus a1, I guess, x plus, let me call that x1, so that's the first x variable, plus a2 x2. Now, to make this look a little more familiar, let me do this, and this, and this, this, and this. So now we have this kind of equation. Now, the thing is that we don't have this. We don't have that. Okay, this would not be called linear regression anymore, because this would be the square of x1. That's not called linear regression. Although we saw that in Weka they create models like this, but they're not called linear models anymore. But suppose we don't have this. So this is still called a linear model. So we could have this variable would be 1, and another variable, then we can have another and another and another. So that would still be called linear as long as none of them were squared or cubed, things like that. So, I mean, linear is just kind of a name, and that's what we mean. We mean none of them are squared, and none of them have other kinds of strange symbols. So, anyway, so that's what we have here in this model. So we have passenger numbers just like we had here, y, or y. And then we have some other variables like the month and the date remapped, which is new date. And this is another one, lag of passenger numbers, but lagged by 12. And then the b is here, or the a sub 0, that here is called a sub 0, is here. So that is the model that we have. Now the only last thing that's confusing is this kind of weird notation here. Actually, I wasn't quite sure what this notation meant, because it has a comma here. Typically a comma in this kind of scenario means and, August and July. But actually it means August or July. So what this means is, if the month is August or July, then month equals 1, or this whole thing is, we might think of this as the variable name, then this whole thing equals 1, and otherwise it's equal to 0. So if it's August or July, then we multiply 12.7 times 1, so we get some, I guess we would say we get a bump in the passenger numbers. It would go up by 12.7. And if it wasn't August or July, this whole thing here would be 0, so we wouldn't get that bump because the whole product here would be 0. So that's what this means. So then you can understand basically this means if the month is any of these, then you get this bump. And if it's any of these, you get this bump. Now some of these might be, here's September and here's September. So if it's September, you get a bump from this factor and another bump from this factor. That's what the model predicts. Okay. And then going back to this model here, then it's really a mess. It's really messy. So we get all of these. Anyway, that's what this model means here. So you get all these bumps, so to speak, but these are actually negative numbers, so they're kind of drops. But anyway, we get all these factors. Then they also included this, and it turns out to be important. We wouldn't have guessed that squaring the date would be an important derived variable. But somehow, according to the attribute selection machine algorithm that it uses, this is useful. And this, in fact, even this is useful. And then one more thing I guess we can mention, and that is here's another factor. So I saw some student projects where people created derived variables that were products of other variables. And if you go through my comments, you'll see that you'll see other students who did that. So it turns out that that's what they do that here. They have the date times this thing as one of the derived variables that Weka creates, and not only that, but it does create them. We can see that they're created here. This times this. You can see the times here. This times this. But not only that, but it's actually included in the model. In other words, attribute selection thinks that it's useful. Okay, so that's what we get here. So that's what this whole long, complicated model is. And then we can go and look at the results, but it doesn't tell us the results because we didn't select here to evaluate the training. So we can try it again, except that I took out the lag creation. So I won't use custom, I guess, and try it again. And now we get evaluation of the training data is quite low. Here, 10. Okay, but then he points out in the video that this is not so great because we don't care about evaluation on the training data. We only care really about evaluation on the test data. So then we have to go back to evaluation and hold out some data for evaluate on held out training. No, that's not what we want. Well, yeah, I guess it is what we want. So we can do that, and this is holding out 30% of the data, but let's just hold out, like he does, 24 months. So you can type in 24 to do that, and then try it again. And now we have, on the last 24 months, we have what the error is. So the root mean squared error here is 19, whereas on the test set, on the training set, it's about 10. So he's not happy with that. He calls this overfitting because it works very well, so to speak, on the training data, I guess we could say not nearly as well on the test data. So that suggests overfitting. So I'll let him go on to explain what else he does, but and also to explain these pictures. So I'll let you go through his videos to do that.